It's a pleasure. I always say the sentence, it's a pleasure to present the speaker, and today is even a greater pleasure than normal because Pieter is a collaborator of mine. I met him at the University of Sydney when he was still a student of Nalini Yoshi, and now he's a postdoc at CISA. And we will speak about our joint work on the asymptotic distribution of roots of generalized Hermite polynomials.
Thank you very much for the kind introduction. Hello, everyone. So I'll be talking about a basically very classical topic, computing the zeros of polynomials. The polynomials themselves are a very ancient topic, but the polynomials themselves are a little bit less ancient. They're about 40 years old. And they're interesting because they define rational solutions of Painlev equations. But yeah, I'll explain it a bit better soon. So first I'll talk give a bit of context. I'll explain what Painlev equations are and Painlev functions. Then I'll introduce the main problem that David and I tried to solve. Then I'll tell a bit about our approach, and finally the results. So I guess any introduction to Painlev equations or Painlev functions should start with special functions. So here's a bit of a sloppy definition of special functions from Wikipedia. So they are particular mathematical functions which have more or less established names or notations due to their importance in applications. And I got this beautiful this quote from a beautiful book, which says Painlev functions are the nonlinear special function of the 21st century. And this quote is a little bit biased, I guess. But it's true that you find Painlev functions in many applications which involve some form of nonlinearity. So from general relativity to random matrix theory to quantum mechanics and so on. So what are Painlev functions? So maybe, yeah, I should start with talking a bit about classical special functions. So when I think about a classical special function, it's mostly like an analytic function which solves some second order linear ODE, and it has an integral representation. So here you have the hypergeometric function, satisfies the hypergeometric equation, and has, for instance, this integral representation on the unit interval. And so it's very intriguing question whether you can maybe define new special functions by the use of nonlinear ODEs. But there are some analytical obstacles, because when you look at a linear differential equation, you can immediately see, just looking at the equation, where the solutions might be singular. So for instance, here we have the hypergeometric equation, and we know that any solution can only branch at 0, 1, and infinity. But when you look at nonlinear differential equations, then you can have movable singularities. So for example, here we have just a simple first order nonlinear equation. General solution is written over there. And what you see is that z is minus 1 is a fixed branch point of the equation, but z is minus c to minus 2 is a movable branch point. So it depends, the location depends on the Cauchy initial data. And so the problem is that if you take a nonlinear ODE, then if you fix some Cauchy data, then a local solution does not define a global function. And so Painlev and his colleagues around 1900 decided to, because of this, they decided to try and classify all nonlinear ODEs which do not have movable essential singularities or movable branch points. And so they did this in the second order case, and for second order ODEs. And the result was that they found 6 nonlinear ODEs, the 6 Painlev equations, such that any nonlinear ODE which has no movable singularities or no movable branch points, movable essential singularities, can either be transformed in one of these 6 equations, or it can be solved in terms of classical special functions. So these are the 6 Painlev equations. So here Okay, so z is the independent variable, omega is the dependent variable, and the alpha, beta, gamma, delta you see in the equations are just complex parameters. And so for these equations, if you fix the solution locally, then this defines a global function. And today we'll be talking about the fourth Painlev equation. Yeah. So just to recap, so a Painlev function is a meromorphic function. It solves a Painlev equation. And so as I said, like classical special functions, they often have an integral representation. And as it turns out, Painlev functions also have a nonlinear integral representation. And this is through an associated Riemann-Hilbert problem. And I'll tell a little bit more about that for the Painlev 4 case. Okay, so now I'll introduce the main problem that Davide and I tried to solve. So as I said, Painlev equations do not have movable branch points or essential singularities, but they do have movable poles. And so the problem of computing these poles is a long-standing open problem. And only for a very limited number of Painlev functions do we have very strong results on the distribution of poles. So we have some results on Painlev 1, and in particular Davide's PhD thesis is, focuses on this problem. Buckingham and Miller and Bertola and Butner derived some very strong results on rational solutions of Painlev 2. And so today I'll be presenting our results on a rational solution of the fourth Painlev equation. So just to give a pictorial example of why these distributions might be interesting. So here you see the distributions of poles of some particular solutions of Painlev 1. And yeah, there's some very beautiful mathematics behind these pictures. So as I said, today's talk is on Painlev 4, and particularly on rational solutions of Painlev 4. And to make the concept of movable poles more explicit, so here's the exact, let's say, characterization. So for any choice of epsilon equal to plus or minus 1, complex numbers a and b, there exists a unique solution with this Laurent expansion around z is a. So you see that poles of Painlev 4 come in, solutions of Painlev 4 come in two types. So either residue plus 1 or minus 1. And yeah, they're clearly movable as you let a vary in the complex plane. So when we're looking at rational solutions, and particularly rational solutions of Hermite type, so we're looking at a family, a countable family of rational solutions. They are indexed by two integers, m and n. And so this rational solution, omega mn, is the difference of the logarithmic derivatives of two generalized Hermite polynomials. And these generalized Hermite polynomials they're defined as this determinant, where the entries are derivatives of the standard Hermite polynomials. And what you see is that the poles with residue plus 1 of the rational solution are zeros of hm plus 1n, and the poles with residue minus 1 are zeros of hmn. And so the problem of computing the distribution of poles is equivalent to computing the distribution of roots of these polynomials. So here are just some explicit examples of these generalized Hermite polynomials. And so the degree of hmn is m times n, and they've got like a symmetry which allows you to swap the integers m and n. And now one of the main problems that we tried to solve is, so Pieter Clarkson in 2003, he published some numerical investigations in these polynomials, and so he observed this structure in the complex, in the roots, in the complex plane. So what you see here, you have the roots of h and n, where n is fixed equal to 5, and from left to right, m is 5, 7, and 9. And so the zeros seem to kind of lie on a almost quadrilateral grid, or a lattice. And so the m parameterizes the number of columns of the zeros, it seems, and n parameterizes the number of rows. And so yeah, the problem is to try and understand what is happening here. And this is the same, some pictures of larger values of m and n. So the problem is to try and understand what is going on. And there's a second problem that David and I were interested in. So what we want to do is kind of let the degree grow large, but fixing the ratio of m over n, and then see, so when we do that and we rescale the roots a little bit, then they seem to like densely fill out some compact region in the complex plane. So specifically, we set this capital E equal to 2m plus n. We fix n as e times nu, so nu is some positive real number. And then what we want to do is we want to send e to go to infinity, and we look at the roots of h and n of e to the power half z. And so it seems that the roots condensate in some compact region. And the problem is to try to compute this region and to prove that indeed they densely fill this region. So here's an animation where we fix the ratio of m over n equal to 1, and we let e grow. So what you see is they start to like so they seem to like kind of like densely fill out what almost looks like a quadrilateral, but not quite. And should be another one, yeah. And similar here we have the same principle with where we fix the ratio of m over n is equal to 3 and 2. And so they again seem to densely fill out some quadrilateral, which depends on this ratio or on the value of nu. Okay, so before I'll explain our approach to try and solve this problem, I'll just give briefly one kind of application in orthogonal polynomial theory. So if you consider the weight function, which is w, which is x to the power of m, e to the minus x squared, e to the power of 2i zx, where now m and z are parameters. And we compute the end Hankel determinant of moments. Then this is equal to generalized Hermite polynomial HMN times some exponential function. So what it means is that if you try to find some a sequence of orthogonal polynomials with respect to this weight, the generalized Hermite polynomials give you the exact condition for which this is possible. So it is not possible if the parameter z is a 0 of one of these Hermite polynomials h and n. And I'll come back to this application later on. Okay, so now I'll discuss our approach to try and solve these problems. So I'll first give a bit of an overview. So first we apply what is called the isomonodromic deformation method. And the result of this is that we find that roots of these Hermite polynomials, generalized Hermite polynomials, are in one-to-one correspondence with some biconfluent Hoyne equations, which satisfy some monodromy conditions. And so, with this information, we can now study these. So we can translate the problem to the biconfluent Hoyne, to a problem on biconfluent Hoyne equations. And these we can study asymptotically using WKB methods. And then finally, what we see is from the WKB analysis, we see that as e goes to infinity, we see that the original problem translates to a specific model problem, which we can solve explicitly. And then by going back, we find finally the distribution of zeros of these polynomials.
This equation is a Jacobi equation, something like this. It is C second. Like in semi-classical limit, the Gaussian case.
I'm not sure if it's. Do you know Davide? I don't.
The equation which appeared in the second term of the expansion after the classical one.
Well, you will see that.
So in the 80s, the Japanese school of mathematicians, they found that these Painlev equations, they govern deformations in some classes of linear systems which preserve the monodromy of the system. And so I will not explain it in detail, but the point is that from this we find that just like classical special functions, the Painlev functions have a nonlinear integral representation, and this is through our Riemann-Hilbert problem. So with each Painlev function, we have associated the Riemann-Hilbert problem. And in principle, computing the solution of the Riemann-Hilbert problem, if you compute the solution, then you get the value of the corresponding Painlev function. And so at a movable pole of one of these Painlev functions, what happens is that either the Riemann-Hilbert problem does not have a solution, or the solution is degenerate. It is of some specific, it satisfies a specific condition. And this allows us to kind of to map movable poles in a one-to-one way to confluent versions of Hoyne equations. Okay, the coloring is a bit off, but so in the case of the generalized Hermite polynomials, if we go to this, if we work out the details, what we find is the following classification. So if you fix some integers m and n, then the point A in the complex plane is a root of the generalized Hermite polynomial HMN. If and only if there exists a B such that this B confluent Hoyne equation satisfies two conditions. So the first is the so-called apparent singularity condition. So if you look at the equation, it has two critical points. So lambda is equal to infinity and lambda is 0. And lambda 0 is a Fuchsian singularity. And it's a resonant Fuchsian singularity. And so the apparent singularity condition is that the singularity is apparent, so that means that if you compute the monodromy around the singularity, it's trivial or it's scalar. So you take a small loop, and if you fix a solution, take a small loop, you get the same solution back up some minus sign perhaps. And the second condition, quantization condition, is just the condition that there exists a solution to this boundary value problem. So there's a solution on the positive real line which vanishes both at 0 and at infinity. And so what this means is that computing the zeros of these generalized Hermite polynomials is equivalent, let's say, to solving, computing B-confluent Hoyne equations which satisfy these two conditions.
Why is it a quantization condition?
Well, it yeah. So, because if you work out what the condition, well, asymptotically what it means is that you get how shall I explain this? Well, yeah, okay. Yeah. I'll come back to it. I'll explain it in a... So, okay, so we want to kind of rescale this problem a little bit for our for the WQB analysis. So I already introduced this large parameter E, which is 2n plus n. We rescale A and B in terms of alpha and beta, and nu is equal to n over E. So then our problem is the following. So Z as alpha is a rescaled root of HMN if and only if this B-confluent-Hoyne equation satisfies the parent singularity and quantization condition. And so the next step is to analyze this B-confluent-Hoyne equation as E goes to infinity using WQB. And so the main idea is that as E grows large, the solutions of this equation get well approximated by WQB functions. So these functions psi, which are like v to the minus 1/4 times the exponential of a elliptic integral. So we have an integral of the square root of this potential v. And so using the fact that we can approximate solutions with these WQB functions, we can translate this apparent singularity and quantization condition into a set of conditions just on this potential, which does not depend on E. So we got one geometric condition and two analytic conditions, which I'll introduce. So I'll first introduce the conditions, and then I'll introduce a geometric condition, then I'll explain a bit about the WQB analysis, and then we'll see what the analytic conditions are. So in the WQB theory, Stokes lines play a very important role. So they tell you where your approximation is valid and where it breaks down. So considering this potential, then the Stokes lines are defined as like level sets, where the real part of this, the integral of the square root of v remains 0, where from lambda star to lambda, where lambda star is any 0 of the potential. And the Stokes complex is the union of all the Stokes lines and the zeros of the potential. So here's an example. So in the case where alpha and beta equal to 0, potential becomes very trivial. The potential of v is lambda squared minus 1 minus nu squared on 4 lambda minus 2. So we can explicitly draw the Stokes complex, and it takes this form. So lambda 1 to lambda 4 are the zeros of the potential, and these Stokes lines that are emanating from lambda 1 and lambda 4, they go to infinity. So, and now the first condition that we have to impose on the potential is that the Stokes complex of the potential is homeomorphic to the one you see here, near at 0, 0. So this is one of the conditions of the model problem. And for the analytic conditions, I have to introduce some cycles. I have to define some elliptic integrals. And so first I have to do some cycles. So if you consider this elliptic curve, so this is just, so p squared is equal to, so this is just, so the elliptic curve is this one. And so, okay, so if we know that our potential, if the Stokes complex is of this form, then what we can do is we can rigidly define two cycles on this elliptic curve. So we do it as you see in this figure here. So gamma 1, gamma 2 are the cycles. And so gamma 1 lies in the sheet where p goes like nu on 2 as lambda goes to 0, let's say. So we've got these two cycles. Now, so I would like to introduce two complete elliptic integrals, S1 and S2. So we take the pullback of the square root of v d lambda. So we get this meromorphic differential omega. And S1 and S2 are these complete elliptic integrals along gamma 1, gamma 2, so along these cycles over here. So in the WQB analysis, asymptotically, these complete elliptic integrals show up. So I'll give one example of a WQB estimate. So if we cut the plane along the negative real axis, and we let psi 0 and psi plus infinity be the solutions of our B-confluent equation, which are, so psi 0 is the one that vanishes as lambda goes to 0, and psi plus infinity is the one that vanishes at plus infinity. So then the quantization condition we had was that the Wronskian of these two is equivalent to the fact that these two are proportional, so that this Wronskian vanishes. And so the WQB estimate, so we obtained the following WQB estimate on this Wronskian. So if you fix any compact set D, on which so for all alpha, beta, and D, the Stokes complex, so the geometric condition is satisfied, then after some normalization, we have the following estimate. So we have a uniform estimate of the Wronskian as E goes to infinity. And so what you see, so the quantization condition as E goes to infinity becomes a condition on the complete elliptic integral S1 that we see here. So if you let E go to infinity, so the thing goes to 0, and then the quantization condition translates to this condition on the complete elliptic integral. So so the quantization condition is asymptotically equivalent to this S1 taking quantized values. So it takes value I pi j divided by E, where G is in m plus an odd number. So why is it a quantization condition? Because well, one explanation would be that this S1 now is quantized. So the condition quantizes this. That's my interpretation, at least. So in a similar analysis of the parent singularity condition, which is a bit more involved, we find that it's asymptotically equivalent to the value of S2 quantizing. So S2 is equal to I pi k on E, where k is n plus an odd integer. Okay, so now if we just look at the Stokes geometry of the potential and we apply the residue theorem, we find that the ranges of S1 and S2 are very restricted. So the imaginary part of S1 lies in this interval, and the imaginary part of S2 is in between minus nu pi and plus nu pi. So if you combine that with the quantization condition, for example, so asymptotically, so we see that this integer j has to take value in the set Im, because Im is the set which goes from minus m plus 1 until plus m minus 1. And the same for the integer k that comes from the parent singularity condition. And so what does it mean? So asymptotically, we have the following model problem. we fix some m and we set e is 2m plus n, and n is e times nu. Then for any two integers j, k, which are in this set, introduced before, we want to construct a potential such that the Stokes complex is homeomorphic to the one at 0, 0. And we have these two analytic conditions. So the imaginary part of S1 and imaginary part of S2 are as prescribed. And so the WKB analysis, what it says heuristically speaking is that the solutions of this model problem are good approximations of the solution of the apparent singularity and quantization condition. And so a good thing to observe here is that basically we've got, for any j and k, we've got a model problem. And so j and k, they run to the set im times in. So we have precisely n times n model problems, which is precisely the degree of generalized Hermite polynomial HMN. So that's accounting checks out at least. So and this model problem we can solve explicitly. So so what we do is we define R as the subset of C2 where the geometric condition is satisfied. Let K be the closure of R. So we had this mapping, we define a mapping S from R into R2. So we take just the imaginary parts of these two complete elliptic integrals. And then the first, well, one of the results we obtain is that so R is a regular smooth two-dimensional real submanifold of C2, and the mapping S maps R diffeomorphically onto the interior of this quadrilateral you see here. And we have a unique extension of this mapping from S going from K to the quadrilateral. So we have an extension to a homeomorphism S from K to Q. So what does it mean? So for any J and K, if you look at our model problem, so we had to ensure that the imaginary part of S1 and imaginary part of S2 are as prescribed here. And we can just, I mean, the solution is just taking the S inverse image of these values, pi j on E and pi k on E. So this is the exact solution of our model problem. And this mapping S is, I mean, this is a completely explicit, this is just some complete elliptic integrals. These are just classical special functions, let's say. And so the WKB analysis, what it says is that these alpha tilde, the solution of the model problem, are approximations, good approximations of the roots, of HMN e to the power half z. Okay, so now I'll talk about the results that we got from this. So first of all, I introduced this set R, and K was the closure of this set R on which the geometric condition is satisfied. So the Stokes complex is homeomorphic to the one at 0, 0. So we project it onto the alpha plane. So we get this, we get a compact set, we get a set Ka, and we call this set the elliptic region. And so by definition, we see that the WKB approximations of the rescaled roots of HMN lie in this elliptic region. So now we have the following theorem on the elliptic region. So firstly, as e goes to infinity, the roots densely fill up this region. So that's good. That's what we wanted to. That's what we expected. And secondly, basically, this region is very explicit, so we can really explicitly, let's say, write it down. So this region Ka is a compact quadrilateral domain. The boundary is a Jordan curve. It's composed of 4 analytic pieces which meet at 4 corners, as you see in the picture here. Now, first of all, the corners are the corner CK is the unique root of this octic polynomial in the kth quadrant of the complex alpha plane. So this is a completely explicit characterization of the corners. Now, to characterize the smooth edges is a bit more involved, but so what we have to do is we have to introduce these algebraic functions. So we introduce x and y depending on alpha. They satisfy these 2 polynomial equations, and they're fixed by some asymptotic behavior at infinity. And so we fix these. So if you have the elliptic region, so we have these corners. What we do is we introduce a branch cut here and branch cut here. So the first point is that we can analytically solve these 2 algebraic equations on the complex plane minus these branch cuts. So cut along these branch cuts. Then if you define this function psi of alpha, which is just the real part of some logarithms involving algebraic functions, this function psi is a univalued harmonic function on the same cut complex plane. This is just, well, it's a bit of some analysis, but it's, okay, so we have this harmonic function, and the point is that the level set where this function is 0 consists of the boundary of the elliptic region, and in addition, some lines which go, which emanate from the corners and go to infinity. So this function psi is completely explicit. You can just put it in Mathematica or something like that, and you can explicitly, like, you can just plot these, this boundary. And so here I should mention that Buckingham, in 2018, he obtained a different parameterization of the same elliptic region. And what he did is he analyzed the orthogonal polynomials that I introduced before. So he studied this problem using the Riemann-Hilbert approach. And he showed that there are no roots outside of this elliptic region asymptotically. So now in pictures, so here we have our results. So here we have the elliptic region. So again, the same animation. And what we see is that indeed, like, it fits very nicely. And here the same thing. So this, So depending on nu, we have this nice description of where the roots, let's say, condensate in the complex plane. And so what we also wanted to know is how do they, what is the distribution of the roots within this elliptic region? And so to describe this, I have to introduce a function SA. So before I introduced this region K and Ka, the elliptic region, which was the projection of K onto the alpha plane. Now a couple of facts that we proved is that the projection from K to Ka is a homeomorphism. And before I mentioned that this mapping S maps K homeomorphically onto this quadrilateral. So if you take the composition SA, so it's S composed of the inverse of projection. So this maps the elliptic region, which you see on the left here, homeomorphically on the quadrilateral Q. And it does so mapping corner to corner and edges to edges. And when you restrict it to the interiors, then it's a C infinity diffeomorphism. And so I'll explain our asymptotic result heuristically first. So we had these exact solutions of our model problem, alpha tilde and beta tilde. And so the WKB prediction, so if you see these alpha tilde, they lie exactly on the vertices of this deformed quadrilateral lattice, which consists quadrilateral lattice consisting of these lines. So maybe I should. So what we do is I should be stretched a little bit like this, but so the alpha tilde are the inverse images of these points pi j on E, pi k on E. So this is Q, this is the elliptic region. So the images of the alpha tilde lie on this orthogonal of a quadrilateral grid, it's quadrilateral lattice. So we take the SA inverse image of this lattice, and then we get a deformed lattice in the elliptic region. And the WKB prediction asymptotically, it says that the roots lie approximately on the vertices of this deformed lattice. And so I'll just show it in a picture first, perhaps. So here we've got on the lower, below we have the quadrilateral Q, and above the elliptic region. And so you see in the elliptic region in purple we have the deformed quadrilateral lattice. And superimposed or in blue are the exact locations of the roots. And see also already for m and n equal to 2, the exact location is almost identical to the vertices of the deformed lattice. Yeah. Now, the exact result is a bit more involved to describe. But I guess the point is that we have explicit error bounds. And so on the one hand, we know that each WK prediction, each alpha tilde approximately is very close to a root of HMN, and also that we cover almost all of them. So that we cover almost all roots of the generalized Hermite polynomials asymptotically. So, however, we have to, in our results, we have to stay away from the edges and from the corners a bit. So it's not really visible in the picture, but actually the roots in the corners are actually slightly off of the prediction in the corners. They do not, the WK prediction fails at the corners. So there's actually the error there, blows up near the corners, and so, or even though you can't see it, the WKB prediction is not, does not match with the exact location of the corners, of the roots. So here's a bit, somewhat larger picture of our results. Now, as to the future, we would like to refine our methods and try to tackle like similar problems for more complicated families of solutions and try to understand the distribution of poles and these kind of things. But for now, I'll just give one example of a problem we're working on at the moment. So they are Okamoto rationals. So they're also rational solutions of the fourth Pandava equation. And so we have a solution expressed in terms of these polynomials q and n, where m and n are now in z, so they're integers. And so again, the problem of computing the pole distribution is equivalent to computing the distribution of the zeros. And so here is a picture of, for example, the roots of q 14, 14. And so the same problem again arises, like, can we understand what's happening in the pictures? And so we're working on this at the moment, and we got some preliminary results. So we kind of think we understand, let's say, where the roots condensate asymptotically, but we still have to do some, tackle some problems concerning WKB asymptotics. So that was it. Thank you for your attention.